Okay, welcome to Lecture XX. This is not a lecture that I have a PowerPoint for, or at least not generally. And what I'm going to do today is I'm going to work a couple of problems on hydraulic losses in pipes. We've already covered this material, so this could be seen as a review, maybe not. Basically, what I'm going to try to do is bring it all together. Okay, there's type 1, type 2, type 3 problems, HDL and EGLs, and I can promise you on the test that you will have an HGL, EGL. It's happened every single time. It will happen this time. And you will have one, type 1, at least one, type 1, type 2, or type 3 problem. It's usually been a type 2 because it's important to me that you study and make sure you know how to iterate. And type 3s are a little bit more time involved than type 2. But it could be a type 3. It also could be a type 1. So I guess it's probably 70% likely it's a type 2. 15% likely it's a type 3, 15% it's a type 1. I don't know. I haven't made up the odds. I guess it depends on how the rest of the test looks, and all that other stuff. But so it's a pretty significant possibility that you're going to have to iterate. Okay. And before I get all the way into this, I just wanted to say that on the exams, especially if time is concerned, but it doesn't even really matter. Given required solution is not required. Okay. A lot of you ran out of time on the last one. And some of those of you who ran out of time were doing given, required, and solution. On an exam, don't worry about that. Okay, I like having that. Part of that is just helping you organize and that sort of thing. And then another part of it is I'm trying to give you free points. On an exam, I'm not going to give you free points for that. If it helps you solve the problem, then by all means do it. Okay, and I would say the same for the free body diagram. I don't think the free body diagram is ever a waste of time, but it is not required. Okay, if it helps you solve the problem, then by all means do it. If not, then don't do it. All right, so as I was preparing this lecture, I was kind of looking around and I was like, okay, well, what are we going to do? And so I was looking for some good problems, and so I found this chapter textbook by Henrik Kudela, however you say this guy's name, and it's on hydraulic losses in pipes. And so we're going to work some of the example problems in this particular textbook. If you want to look up how they do things and how they organize things, it's pretty well done. But I'm going to mention one particular thing in here before we move on. If I zoom out, you're going to recognize a lot of this as being kind of the same things that we have in our textbook. So, for example, if I go all the way over here, you'll see the Colebrook equation. So that's the equation that is Moody. Okay, and if we zoom out, we could zoom in over here and you see Moody. Here's Moody. It's a simpler Moody. It's not so messy as yours. Yours has all kinds of stuff all over it. One of the things that I want to mention here that that I haven't, I've probably mentioned, but I don't know for sure. Okay, and is this. Okay, on your Moody diagram in your textbook, one of the key things over here is this over here, and this is the relative roughness. So this is, I'm going to say in your text, this is what happens. Okay, epsilon is the relative roughness, equals Ks on D. Okay, in this particular in this text, okay, there is no symbol for the relative roughness. It equals epsilon over D. Okay. The reason that I'm mentioning that is that this Ks in your text is the same thing as the epsilon in this text. Okay. So what will happen is, if you're, and you can kind of see it in this equation right here, epsilon over D. Okay. That kind of really, I'm going to kind of zoom in to make sure you can see what I'm talking about here. But that epsilon over D, which is this guy right here, okay? This epsilon that is, usually our Ks, but it's got units on it, okay? So with an exam or anything that you might see, it's going to tell you a certain number of, say, millimeters or something. So then you're going to put your diameter in millimeters, and it's going to all cancel out, and it's going to be the relative roughness. And they don't even have a letter or anything for it, okay? It's just telling you where to be. So if the ratio of the roughness elements, the diameter is 1 to 100, well, then you're right here on this line, okay? Now, the real reason that I mention this is that you're, like, well, why do you care what they do in this textbook? Who cares? Well, because this is how the FE does it. Okay. So what I would recommend to you is that you flip through the FE, equations, and you find Moody, and you will find that this is how the FE does it. So they're going to give you an epsilon, okay, and the epsilon in this case is the same thing as our KS. Okay, and obviously the D is the same, and they don't have a symbol for the relative roughness, so I just kind of think of it as RR. Okay, so just be aware that's out there. It has very much has the potential to confuse you on the FE. Now you'll say, well, why did you even teach this version? Well, unfortunately, that's the text we have. And I didn't want to confuse you by going contrary to the textbook. Some of my students use the textbook to learn, which is great. I'm really, really happy about that. Anyway, so, and again, we can see right down here, notice the roughness. It's, the roughness, instead of being KS, it's epsilon. It's not any different, it's just a different letter. Okay, and unfortunately, epsilon is used two different ways by the different texts. So just be aware of that. Okay, so we are going to work. I'm going to zoom out, and I'm just going to pause it, and we're going to zap over to the problem we're going to work. All right, so here I'm going to work this problem, and what you can see kind of ahead of time, depending on how you look at this, is that I have arranged this as best I can with all the tools that I'm expecting that I'm going to need for really kind of any Moody diagram problem. So the first thing, obviously I'm going to need Moody. These are my Ks for the minor losses. And these are my roughness elements for the rest of it. Okay, so what we're going to do here is we're going to find the discharge through the pipeline shown for H equals 10 meters. Now, what I want to kind of be very aware of is that in the second one, they said the head loss if Q is 60 liters per second. If Q is 60 liters per second, so I'm going to just go ahead and convert that real quick. If Q is 60 liters per second, or 0.06 cubic meters per second, that means H is no longer equal to 10 meters. So in this case, H does not equal 10 meters for part B. Okay, because obviously you can get pretty much any flow rate you want out of here, depending on how high you make H. Like if you make H 1,000,000 feet, you're going to get you can have a tremendous amount of head loss, but you're also going to get a really high flow rate. So let's go ahead and let's work this problem. The discharge through the pipeline shown for H equals 10 meters. Okay, so this is always nice when they do this for us. They don't always do this for us, but look, they gave us our points. So here's one. I'm going to delete that because I just really messed that up. So we will delete that. And anyway, so we've got our points 1 right here and 2 right here. Okay, so here's our energy equation. And again, as with the usual tools, geometry. Well, we always need geometry, but continuity isn't really going to come in here very heavily. Hydrostatics. There's no manometers or anything like that. Momentum equation. We don't have any forces on moving fluids. There's nothing in here either giving any of those or asking any of those. So there's no real ways that we can use those. So we're going to go from 1 to 2, and we're going to do this in the standard way that that this always works for us. Okay, so at 1 atmosphere, at this point, hopefully, this is becoming old hat for you. Okay, Z1. Well, I guess it depends on where we put our datum. I think. Probably the easiest place to put it mathematically would be to put it at 2. Okay, you could put it down here if you wanted to, but I'm going to put it here, okay, because I think that's going to make my life easier. Okay, so Z1 would then be 10 meters because we're 10 meters above the the datum, and then Z2 is going to be 0. Okay, we like that. We always like zeros. Okay, and then for this velocity, well, this is 0 due to the tank assumption or the Tahoe assumption or whatever we want to call it. V2 over 2g is unknown, so this is unknown. Okay, we don't know that velocity a priori or beforehand. Okay, there's no pump, there's no turbine. And, well, what's the head loss? Well, we don't know what the head loss is, right? So that's kind of where we're going to drive, where we're going to kind of get at, okay? So if we simplify this, we get 10 meters equals alpha V2 squared on 2g plus the head loss, okay? And of course, we're going to split that head loss out into the friction loss plus the minor losses, okay? So the friction loss is F L on D V squared on 2g. And the minor losses is the sum of the k's, okay, times v squared on 2g, okay? So one nice thing here, if we look at this right-hand side, is that everything is v squared on 2g, right? The pipe has the same diameter through the whole way, so, that's really, 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 really nice. Okay, so this thing right here, okay, is the same throughout the whole thing. So technically, we could write this as 10 meters equals alpha plus FL on D plus sigma on K, all that in parentheses times v squared on 2g. Okay, it's not really critical that we do it that way, but we could do it that way if we wanted to. Okay, so instead, I'm going to start focusing on, what do we know, what can we work with, et cetera, et cetera. And one of the things that I want to do here, and we're gonna have to test this at the end. I don't really like that alpha, so what I'm going to do is I'm going to assume that alpha equals 1.0. Okay, so that assumption is basically, that we have turbulent flow. So I'm going to need to check that at the end. Okay, so that's in red. So we need to check this assumption once we get the velocity, right? Once we have the velocity, we've solved the problem. So let's hope that we got it right. So we will get to work on that. Okay, so the rest of these things, if I kind of mark in green what we know, okay, we certainly know the length of the pipe. Okay, it looks like L is it's 30 going this way, 12 going that way, and 60 going this way. Okay. We know the diameter of the pipe, 150 millimeters, so that's 0.15 meters. And then we know these Ks, or we should be able to get at these Ks. So where are our Ks coming from? So we've got quite a few Ks. We've got a K right here, okay, at this square-edged entrance. We've got 2 standard elbows, okay? And then we've got a globe valve. Globe valves have a rather large K. So let's go ahead and I'm going to just, well, you know what, let's go and look for these. Okay, so the square-edged entrance. Let's go over here and let's look what we can get for a square-edged entrance. Okay, let's see what we get. Okay, pipe entrance. Okay, here we go, pipe entrance. Well, let's see if I can zoom all the way in. Okay, pipe entrance. So we've got a square-edged, so that means it's doing like that, which means it has no radius, which means radius over diameter is 0, which means for a square-edged entrance, we get 0.50. Okay, 0.50. Okay, so let's go back over here. Let's see, a square-edged entrance. So this one right here, this is going to have 0.50. Okay, the globe valve. We're going to go back over to our chart down here. Globe valve wide open. Okay, 10.0. Okay, we're going to assume that it's wide open. They don't really give us any other options, so we're going to have to go with that. Okay, so we'll go back over here. The globe valve will be 10.0. And then this last one, we've got 2 standard elbows. Okay, and so if we go down here, these are 90-degree elbows. Now, don't worry, on an exam, I will make sure that the language matches up exactly. In this case, I got an elbow that, this chart is from your textbook. The question is from another textbook. So, don't sit there on the exam and go, wait, is this the elbow that I need? If on your exam, if I give you an elbow, I'll either call it a 90-degree elbow, or I'll say, this particular elbow has a K of blah, blah, blah. Okay, so those both have a value of 0.9. Okay, so let's go over here, and we'll say 0.9 and 0.9. Okay, so we've got the K's, we've got the L, we've got the D, and now we've got F, and we've got V. Okay, so this is the point where things start to get interesting. Okay, so I'm going to write this, I'm going to simplify this one more step. So we've got 10 meters equals, we're assuming alpha is 1. Maybe I'll write that in red so that we can remind ourselves that that is a 1. Okay, and then I'm going to, pull things out front, plus F, okay, L on D. Okay, so we said that L was 30 plus 12, which is 42, plus 60. So that's going to be 102 meters over D, 0.15 meters. Okay, plus the sum of K's. Okay, so the sum of K's is going to be 0.50 plus 2 times 0.9 times that globe valve, 10.0. Woo! That's a spicy meatball. All right. So then we're left with V squared on 2G. I'm going to ignore the overbars for the V's because I don't feel like writing them. But it is, it does indicate that this is the average. Okay. So, so if we write that all out, we get 10 meters equals 13.3 plus 680 F, okay, times V squared on 2G. Okay, now this is, as we've worked these before, where, these problems they just get dicey, right? So I'm going to go one more step. So I'll take it one further step and I'll say 196.2 meters squared over second squared equals 13.3 plus 680 F times V squared. Okay, and this is it's an ugly equation, but it's one of those where, okay, and this is kind of where I want to back up and start thinking about the types, right? So I need an F. Okay, anytime you need an F, now you're thinking, all right, I'm in type 1, type 2, type 3 territory. And it doesn't really matter what type you are, what the numbers are or whatnot. But what the types indicate really is how many unknowns you have when you go to the Moody diagram. If you're at type 1, that means you just go to the Moody diagram and you read off F. If you're at type 2, that means you don't know one of the axes, okay? And so in this case, we don't know V. Okay, we don't know this. Okay, if you don't know V, then you can't get the Reynolds number. If you can't get the Reynolds number, then use there's one axis that's unknown. If there's only one axis that's unknown, that's a type 2. Okay, if there's two axes that are unknown, that's a type 3. So that's obviously the hardest, okay? So right now what's going to happen is, again, and I've tried to, say this as much as possible. If we go over here to this Moody diagram, okay, and hopefully it's, not blurry. If we go over to this Moody diagram, okay, we have a relative roughness over here. Epsilon equals Ks on D. Okay, and we have a Reynolds number over here. Reynolds number equals Vd on nu. Okay, we can't get the Reynolds number. We can get this epsilon, okay, because we know Ks, or we should know it because they gave us that it was I think they said it was a clean concrete pipe. We'll go back and look at that, and we know the diameter. So the diameter is 0.15 meters, and the Ks is going to depend on the material. So let's back up. Okay, so clean cast iron pipe. Okay, sorry, I said it was concrete. It doesn't really matter. So let's go over here. Here's our cast iron. Okay, we are working in the SI system, so here it is, right here, 0.26 millimeters. So we're going to go down here, and we're going to say 0.26 times 10 to the negative 3 meters. Okay, so it's going to end up being fairly smooth, I would say. And we get zero. Where's my marker? Why would you go away? Why would you do that to me? Okay, 0.00173. Okay, obviously, just like the Reynolds number, getting too many significant digits here is not really necessary. So I normally keep 5. In this case, 2 is going to be more than enough, as you can see just looking at the relative roughness chart over here. All right, so we know the relative roughness. So if we go over here and we say, okay, well, let's just go ahead and find that, 0.0017. Okay, 0.0017, so here's 0.001, here's 0.002, so 0.0017, none of these colors really show up very well on this. Let's just go ahead and do red. Okay, that shows up pretty well. Okay, so let's go this way. And we're, 70% of the way between those two values. Okay, so we're just gonna, it looks like I'm kind of veering too much towards the low end of that, but whatever. Again, you do the best you can. There's really no better way to do it, okay? All right, so we're going to be somewhere, on that line, right? But we don't know where because we don't know this Reynolds number. So what we're going to do down here is we're going to go down to this Reynolds number, and I'm going to say, okay, let's simplify this as best we can, okay? So we don't know this velocity. We know the diameter is 0.15 meters, okay? And then the viscosity of water is 10 to the minus 6 meters, okay, more or less, okay? So our solution here for it's not really a solution, but our easy version of this equation is 150,000 seconds per meter times V. Okay, now you might also be wondering, why do I bother with this? Why bother? And the reason that I bother is that if somebody else were to come in and give you a velocity right here, okay, you could put any velocity in here you want. But what this tells you, if you want to get the unitless Reynolds number, you either need to convert the 150,000 to the same, to the same units as you have for the velocity, or you really should just put the velocity in meters per second, because that's what's going to cancel. Okay, so that's why I bother. Okay. So now I've got an equation to get the Reynolds number from V, okay? And so now we're kind of getting somewhere, okay? So if I go back to my original situation here, here's my equation, and one of the things that that hopefully you would understand at this point is that if you get to this point and you kind of understand that, this is a type 2 problem, then the only thing that you really, then you kind of need to set up your iteration. And iteration always works in the same way for a type 2, okay? And basically, you're going to have to guess. You're going to have to assume an F. And that is the fundamental thing, okay? Once you have an F, you can use that equation that we just put up there to get a V, okay? So we'll call that equation 1. You can call it whatever you want, but it's just to help kind of map what's going on here. I don't really like how I've written it right here, so we're going to rearrange it so it's a little bit easier. We're going to use Reynolds number, the equation we just kind of found out for Reynolds number. That's going to be our second equation, okay? Because if we can use the first equation to get V, we can use the second equation using that V to get a Reynolds number. And then once we have both of those things, we can use Moody to get another guess for F. Okay, so what we're going to do right now is, I don't really like this version of equation 1. So we're going to resolve this with a better version. We're just going to solve for V as a function of F. Since we're going to have to do this a couple times, it's just going to make our lives a little bit easier. So we're just going to, rearrange. So you can kind of see this if it's going to be V equals the square root of 196.2 meters squared over second squared divided by 13.3 plus 680F, okay, which is a lot easier to work with than what we just showed, okay? So it's in green just to kind of highlight, that this is this is the way that we're going to do it. Because all we have to do is plug in an F right there, and the V pops out. Okay, so we'll assume an F. We'll use equation 1. That'll give us V. Okay, once we have V, then we'll plug that into the Reynolds number equation, which we have deemed 2, although it's a little tiny on this screen. And then once we have a Reynolds number, we'll have both the Reynolds number and the... I don't know why this is doing that. Okay, yeah. So we'll have both the Reynolds number and the relative roughness, and we'll be good to go. And of course the relative roughness in this case is easy, or maybe not easy, but we've got our red line, so that's pretty straightforward. Now our guess should follow the green line. Okay, so we want to follow the flat portion of the red line all the way over to the left. Okay, it's not going to be a perfect guess, but it's going to be pretty good. 0.022, right? We should be, cooking with gas. It may not solve exactly, but it's not going to be bad. Okay, so let's go ahead and plug that in. So we're going to plug that into equation 1, and then what's going to kick out is going to go into velocity 1. And the way it's arranged is pretty straightforward. So we get what we get. The numbers aren't really all that terribly important. They are important, but okay. So then we take that velocity, we plug it into the Reynolds number, and then out comes a value for the Reynolds number. Now in this case, this equation is easy. You just take 150,000 and multiply it by whatever the velocity is. So we get 1.6 times 10 to the 5th. And then we now have, we just need to go to the Moody diagram. And so if we zoom in to 1.6 times 10 to the 5th, so 10 to the 5th is like, it's pretty easy. So there's 10 to the 5th, and there's 2 times 10 to the 5th. So there's 1.5 times 10 to the 5th. So 1.6 times 10 to the 5th is a little bit over to the right of there. And unfortunately, we're kind of on the curvy bit. So it wasn't our first guess. So we're going to have to do this again. But if we take a left turn when we hit there and we use our straight edge, we should be able to get a pretty good guess. It looks like we're kind of going to be in the, that was a bit of a crooked line. But 0.024, fine. There's a little play on this, but I think if you look at that, I'm a little bit diagonal. But let's just see if it works, right? So we put that in there. And then we go back and we do this whole thing again, with the goal being that everything will line up for us. So this is just kind of the same procedure, using the same equations, just one more time. So into equation 1, out of equation 1, we get V1, 1.0543 meters per second. We're going to plug that into the Reynolds number equation. And if we're lucky, we'll get the same Reynolds number to 2 significant digits, because we're not going to be able to read that chart better than that. And if we do that, if we do that, what do we get? 1.6 times 10 to the 5th. Sweet. Okay. So that means that, we don't even really need to read the diagram again, because we know that we're going to get the exact same value. Okay, so as soon as the Reynolds number matches, the Moody's are going to match, which means that our velocity, our answer, is that last answer. So, and obviously it's not exact, because the F assumed, the F value is not 0.24 exactly. But this is the best you can do while using the Moody diagram. So if we do continuity from there, we can get the final solution. Which has nothing to do with Sherlock Holmes in this case. But, just doing continuity. And so if we plug all that into the calculator, we get the massive flow rate of 0.0186 CMS, cubic meters per second. Now that, and that's what happens when you have a tiny pipe. You get tiny flow rates. Okay, so cubic meters per second, boom, nailed. Okay, so nothing super exciting here. Well, I guess depends on your point of view. All right, so that was part A. So now we'll do part B. And in part B, I have a little error. well, hopefully you'll get excited when you recognize it. You'll see what it is, and you go, oh, cool, there's an error. I caught it. I saw Wagner. He's an idiot. Anyway, one of the things to note here is that it's giving you the flow rate here, Q. So remember that the H, which is given, you know, if I give you this problem, I'm going to word it a little bit better than this, but this Q, you know, is basically, Q is heavily dependent on that H. Okay, if H is 0, there's going to be no flow rate, right? Because then the water in the tank is the same elevation as the pipe, so it's not going to come out. If H is like 1,000,000, well, then there's going to be tons of head loss, and the pipe is going to be flowing out. Okay, so, but in this case, poorly worded problem, but H is unknown in the second half. So, but, you know, it's okay because the H doesn't even really show up in this. But we'll demonstrate that as we go. Okay, so here we're just going to kind of play with, and the nice thing is we can use a lot of the stuff that we've kind of already done in part A. So let's, you know, we're going to try to make it so that we can see what we did in A. But we're just going to look at this head loss because that's what we're looking for. Let's just see if we can go straight forward, okay? So the head loss splits into these two things, the friction loss and the minor losses. So algebraically, we can, you know, Darcy-Weisbach for the friction losses, and then for the head losses, we're just going to use the coefficients of loss from the chart in the book, or, you know, whatever chart you want to use. And so considering those are the same velocities, because it's just one pipe, we will go ahead and separate that out, okay? And luckily, we can work with that, okay? So we already have done all of this. We're going to have a different F because we have a different velocity in this case, different Reynolds number, all that other stuff. So that's problematic. It's the first thing we wanted to plug in, and we don't know F. Okay, so that's pretty annoying. Just going to have to do the best that we can. Perhaps then, you know, like recognizing that to get F, you know, we're going to need, you know, how do we always get F? Well, we're going to have to do the Moody diagram, okay? We also don't know V, okay? So this is kind of problematic, but one of the nice things about V is that we can just do continuity in this case because they gave us Q, okay? So we're just going to kind of like, you know, Q equals VA, so we'll just go ahead and solve that, boom. Okay, and those 5 significant digits, which are totally annoying, but they're there. And so then we need an F. Okay, so to get an F, we need a Reynolds number, and we need a Moody diagram. So we need to zoom over to the Moody diagram. So let's go ahead, and it's a little tiny here, but we'll zoom all the way in. And what's nice in this case is that the equation that we created earlier still works. Okay, because we have the same. Well, everything we did earlier still works. The epsilon still works. It's the same pipe, the same dimensions. And if we look at the Reynolds number, we have the same viscosity of the fluid, and we have the same diameter of the pipe. So this equation still works. Okay, so I can take my, my velocity that I just solved for, and I can plug it into V. Now, if I'm lucky, you know, I'll get somewhere around the same value I got for the last problem. But that would be poor planning on whoever did this, and sure enough, it doesn't really work out. If I plug in that like 3.4, I get 5 times 10 to the 5th. Okay, so if we find that over on our x-axis, we will note that, lucky for us, we end up in the flat region of the in the fully rough turbulent flow, as they call it in this case. So there's 4, there's 6, there's 5. So we're just going to go up. And we'll hit the line, and we're basically going to follow that green line to the left. If we use a ruler, we'll probably end up in the same spot. I guess it depends on, you know, how good we are at using the ruler. And, you know, basically the same spot. I think my green line was probably more accurate, but it doesn't matter. 0.022. So we'll go back over here to the head loss equation. And boom, plug and chug, knock them all out, okay? Now, what you're gonna notice if you stare at this is that I made an algebraic error here. 89.5, which I was very impressed with when I created this, because it's pretty impressive, turns out to be incorrect. But I didn't notice that. So what I did instead was I noted that we had forgotten to, check to see if the flow was turbulent. You see that big red bit right there. I forgot to check that. So we need to go back in and, right here I'm actually talking about how impressive it is to lose 89.5 meters of flow. And what that kind of implies is that you probably didn't start with 10 meters ahead for part B. But of course I made a mistake and there's actually aren't 89.5 meters. And see if you can see what the algebraic error is. And it might help you to not make that same algebraic error. Okay. In the meantime, let's go ahead and let's sneak over and we're going to check the turbulence, whether or not this sucker is laminar or turbulent. We'll do that in red in order to match the check right here. And we'll just give it a couple seconds while, me from like an hour ago stops rambling on about stuff. Here you go. I'm finally going to do it. Okay, so we're going to check to see if it's turbulent. Again, this is nice because we can use our equation right over there, R equals VD over nu. Okay, so yeah, so we can just use that little equation. Okay, so I'm going to zoom all the way in and let's go ahead and solve. Okay, so our velocity was, what was our velocity over there? I guess our velocity must have been about 1 meter per second. Oh, yeah, our velocity for part A was 1 meter per second. So we just kind of plugged that in and got a rough estimate. Okay, and sure enough, it checks out, it's turbulent. Okay, so at this point, my earlier me was very proud of himself for getting the answer right and was ready to move on to the next problem. However, my current me knows that I made a mistake. And so if we, I think I might have said some goofy things as well. That is, kind of my way. But so if we just wait just a second, I'm going to realize my error. And I think if you look there, you can see it, which is that I plugged in 0.22 as my f, when my f should be 0.022. And I didn't put my parentheses in the right place. So that 0.022 is only being multiplied by L over D. So it shouldn't be multiplied by the L over D plus the sum of K. I will also note that the sum of K here is 12.3, whereas in part A, like you look at it and you'd be like, wait, he's got a 13.3. But the 13.3 was because we had the 12.3 plus the alpha. There is no alpha in the head loss, okay? So make sure that makes sense to you. Anyway, so if I make that algebraic correction, my head loss changes to about 16 flat, 16.01, something like that. There you go. When earlier me learned how to write, crawl out of his cage. Okay, so 16.0 meters would be what we would report. Okay, so that is all she wrote. All right, so here's a doozy. I'll give you a couple seconds to read it if you want. But what I'm going to do, and this is just going to kind of be like a, snap your finger and it goes, is I'm going to just pause it for a second, write down all the givens and draw it out for you. Okay, so but this would be a really excellent problem. This could be something like this could happen for an exam. It has one wording thing which I'm just copying the wording from another source that I just want to point out to you before I snap my fingers and have everything change, which is this thing right here. It says it has an equivalent roughness of 5 times 10 to the negative 7 feet. And we've never done anything called an equivalent roughness. And so the question is this the relative roughness, or is this that sand roughness factor? Is this, is this that KS, or is this the relative roughness? And I left it in these words because I want you to think about kind of what I talked about earlier about, different uses of the word epsilon. And what's important here is that this thing has a unit to it, feet, okay? And so that feet tells it this is the roughness, the size of those little roughness elements on the pipe. Okay, so we want to take that and divide it by the diameter to get the relative roughness. Okay, so that's kind of what we want to do there. Actually, I guess I'll read it to you just to be clear here. Okay, water supply systems being designed for an apartment complex. Okay, so actually let me pause it and I'll draw that. All right, so there's an apartment complex. I tried to make this print really, really large, but just kind of bear with me. I'll zoom in on the picture and tell you the important things here. Okay, so there's a pipe, the city main. It's coming in and out of this board for us. And in the city main, they maintain a pressure of 65 psi. Okay, you're trying to carry that water through this pipe, okay, to your apartment complex. The pipe is a total of 100 feet, so it's not technically, in the straight direction, but whatever. I couldn't figure out how to draw it, so it would squiggle. Anyway, so you're going to want that water to travel along this pipe and up into your apartment complex where people are living and bathing and doing all that other stuff. Okay, and they need 25 psi. Okay, if they don't give 25 psi, it's going to come dribbling out of the shower or out of the faucets or whatever, and they're going to be unhappy. And you need this kind of flow rate. Okay, so that's the gist of the problem. The only other kind of sorry about that. The only other tricky thing about it is it gives us an equivalent roughness, so it gives us Ks, okay, is what we would call it. So that would be 5 times 10 to the minus 7th feet, right? And it tells us, we've got 4 threaded 90-degree elbows. So I only drew 2, but there's 2 more in here somewhere. Okay, 10 threaded unions. So basically that means there's a piece of pipe here, and then there's one right here, and then there's one right here, and there's one right here. And they just use these unions to combine them together. And a swing check valve for forward flow. And I don't really know what that is, okay? But basically the gist of it is that the sum of Ks, if I add up all of these Ks, is I've got 4 times 1.5, okay, plus 10 times 0.08, plus that swing check valve. Okay, so it's going to be 1 times 2.0. Okay, and I can add all these up because they're all going to have the same velocity. Okay, so I can just kind of like do this right off the bat because I know it's going to be the sum of Ks times V squared on 2G. And the reason for that is because the V squared on 2G, these are all going through the same pipe. Okay, so the other thing that we're going to do just to make this problem a little bit easier for ourselves before I move on is I'm going to do all these conversions, and I'm just going to, again, they're just going to pop up for you. All right, so converting everything to standard units. So now we've got cubic feet per second. We've got PSF instead of PSI because PSI is kind of annoying. And let's go ahead and solve this sucker, okay? So again, what this is driving at, as soon as we see, all of these Ks, this particular KS, as soon as we see, this KS, we're thinking, okay, well, we're dealing with energy equation. As soon as we see this, we're dealing with energy equation. But the more important one is this one because that tells us that we're dealing with F. And if we're dealing with F, that means we're dealing with the Moody, okay? And if we're dealing with Moody and we need to get F, then what we're going to need to do, and I'm just kind of like logically working this backwards, is on the Moody, we're going to need to be able to get the relative roughness, which we usually write as epsilon equals Ks on D, right? So that's normally this axis. And then on this axis is the Reynolds number. Reynolds number equals Vd on nu. Okay, note, in this particular problem, we do not have D. Okay, so we cannot get the vertical axis. We cannot get the V here. And because we don't know the D, we also don't know the V. Okay, so this is what we would call a type 3. Now, if we're doing a type 3, what we're going to do, and I don't know how much room I'm going to need to do this, so I'm just going to kind of like put this, down here a little bit, is what we're going to do is we're going to assume a D. Okay, so we're essentially what we're doing is we're assuming an answer, but we're going to assume a D. We're going to assume a D. D assumed. Okay. Once we assume that D, if I go up here and I look at these, kind of like, if I kind of look at this kind of schematic that I drew over here. Once I know the D, okay, once we've got, the D, well then, we should be set up to get epsilon, okay? And, that is obviously pretty straightforward. Okay, so we'll need an equation for that, okay? Let's just call that equation 1. I think in your notes I called it 3, but whatever, And then we're also going to need this Reynolds number. So we're going to need an equation for that. Okay, so we'll call it the Reynolds number. Okay, and that'll be equation 2. Okay, once I have both of those, I can get F. Okay, now the only place we ever get F is from Moody. Okay, and once I've got F, well then, somehow I'm going to have to turn this back around onto D. Okay, and that's going to need a third equation. Okay. Usually what happens here is that this equation right here, that third equation, comes from the energy equation. And epsilon is like, almost trivial. And then the Reynolds number, it's almost like these are going in increasing difficulty. So let's go ahead and get the epsilon equation. By the way, I already can tell you right now, without having really thought about this problem, I'm going to assume a D of 1. Okay, just because that's an easy number. I like that number. So we can do that. Next, let's focus on getting this epsilon equation. Okay, so let's zoom up here. Let's get an epsilon equation. Okay, so we'll do epsilon, relative roughness, equals Ks. What's the given Ks? 5 times 10 to the negative 7 feet. 5.0 times 10 to the negative 7 feet divided by diameter. Okay, so we assume a diameter, we get epsilon. Boom. That's not so bad. Okay, so that's equation 1. Okay? All right, now, Reynolds number. Okay, well, that's equation 1, so we're good here. Now I need a Reynolds number equation, so we're going to zoom in down here, see if we can't get a Reynolds number equation. So let's see, Reynolds number equals, well, we want this in terms of D, right? So that V we're going to write as Q over the area, but it's a pipe, so we'll do pi D squared on 4. Okay, so that's V times D divided by nu. Okay, so that, if we rearrange, well, let's see here. We're going to end up with a 4QD. Oh, I think this is almost the exact same equation we got for the problem in class. It's nice when we have pipes, because things kind of tend to repeat for us. Okay, over, let's see, pi nu. Okay, so with a slight fix there, I had the D in the wrong place. Okay, so this is equation 2, and so that should so boom. Okay, cool. So now we've got equation 2. Okay. Okay, now we've got F from Moody. Okay, no problem. Boom. And now we need D. Okay, D has to be a function of F. Okay, so we need some kind of equation that's going to make D easy to solve for from F. Okay, so we're going to go back up to this original problem up here, and we're going to think about what we've got going on here with all these Ks and all this other business, and we're going to do the energy equation. And because it's really late at night and I'm really tired, I'm going to write it out. Okay, over Z1 plus, but you don't have to watch. All right, so there it is. We'll use a different color to get rid of terms. Okay, so P1 over gamma. Ooh, well, unfortunately, we have a pressure here. So we get so used to getting rid of it all the time that we can't in this case, right? So it's going to be 9360 PSF. Okay, P2 is going to be 3600, excuse me, 3600. Okay, PSF. Okay, Z1, if we make this our datum, is 0, so we'll call that our datum. Okay, so Z1 is 0. Z2 is going to be 10 feet. Okay, and this first pipe and the pipe in the house, we don't really know a whole heck of a lot about what the velocity is going down the pipe. So we're going to kind of make it's not really that interesting an assumption, but basically we're going to make our point right here. So barely inside the connector pipe. Okay, barely inside that connector pipe. So that's going to be pipe 1, or pressure point 1. And then point 2 is going to be barely not inside the apartment complex, 2. Okay, and the reason that I'm doing that is because I don't want to have to deal with these velocities. So if I do that, then they are the same, right? They have the same velocity. So I don't even need to worry about whether or not they're turbulent or not, although, you know, they almost always are. But by putting those points there, by being clever about it, I'm not sure that it was that clever, but, you know, you can save yourself a little bit of hassle. Okay, so there's no pump in this situation. There's no turbine in this situation, but there's certainly some head loss, right? We hate the head loss. You know, get up, get up. We like the head loss, baby. Get up, get up. All right, so the head loss, we're going to have 2 types of head loss. You know, the head loss due to friction plus the head loss due to minor losses. Okay, and so so this equation is ugly. Like, it's uglier than we usually have it. But basically, usually we have a reservoir on the left, and in this case we just have pressurized flow, and that's what's driving it up into the apartment complex. Okay, so let's go ahead and I'll show you one intermediate step here. So 9360 PSF divided by 62.4 PCF, so that'll give us feet, equals 3600 PSF over 62.4 PCF, okay, plus 10 feet, okay, so everything's in units of feet, plus HF, so this is going to get a little bit crowded, but HF is FL on D, V squared on 2G, plus HL, which is going to be the sum of K times V squared on 2G. Okay, noting that the V squareds in this case are both the same, okay, because there's only one pipe. Okay, so let's go ahead and clean up some of these numbers on the left, because that's really not where we're focusing right now. Okay, so there are those numbers right there. And then we have an F, which we don't know. We know the length of this pipe, which is 100 feet. Okay, we know the oh, no, we don't know the diameter of that pipe. Right, so let's zoom in. We don't know the diameter of that pipe. Plus, I'm going to kind of algebraically separate, and then so we have the sum of K's. So the sum of K's is, well, I never even bothered plugging that into my calculator. What a jerk. Okay. But it's, you know, 8.8. So we'll go back down here and we'll say it's 8.8. Okay, times V squared on 2 times G, which is 32.2 feet per second squared. All right. So this is an ugly equation, but it has exactly what we want in it, right? We wanted an equation right here, okay, that was D as a function of V. No, sorry. Excuse me, that was D as a function of F, okay? And we've got D and we've got F. Now, the annoying thing right now, though, is we still have a V in there. We don't want to have a V in there. The V makes our lives much more difficult. So we need that V to somehow morph its way into a D, which we can do with continuity. So I'm going to do some algebra here real quick. Give me a second. All right, so kind of tracking the last equation, I just combined all these first 3 terms here, 1, 2, 3, and then I multiplied by G, okay, or by 2G. So now we've got this, you know, this term right here on the left. And on the right here, instead of V squared, well, it is V, but I'm going to put Q over pi D squared on 4, because, you know, as you guys know, that is the same thing as V. So again, we're going to do some algebra. I'm not going to make you watch me do it. Okay, so again, I've just squared the right-hand side. I've got 16Q squared, and the Q in this case is 2.6738, 2.6738, okay, CFS, and then pi squared D to the 4th. And again, I'm going to kind of combine all of that, and again, I'm not going to make you watch me, so just hold on one second. All right, so if we take that, kind of nasty equation, we rearrange it, we get something that looks like this. And then, if we rearrange that, that's very difficult to isolate D. So I isolated F, which is fairly problematic, I would say. We really needed to isolate D. So in this particular case, it seems to me like that what's probably going to happen here is that this is going to require a computer solver. Okay, so just, I will never ask you to do this. Okay. I will never, I might give you this type of problem, but I will never give you one where solving for D is so difficult, okay? So I will never ask one where, solving where D is not easily isolated, okay? So, but that's just what happened here, okay? So let's see if we can't solve this problem. So I already told you that my first guess was gonna be to start with a diameter of 1. Just because I like easy numbers, okay? Call me a jerk, okay? It's okay, I'm a jerk. All right, so then we're gonna go to epsilon 1, so I'm gonna go up here. Here's my equation 1. So I'm gonna plug in that 1 foot. I don't even need a calculator for that. 5.0 times 10 to the negative 7th feet divided by 1 foot. This is why I chose 1, okay? So I can go over here. My epsilon is 5 times 10 to the minus 7. Okay, what's my Reynolds number? Okay, so we're going to go over here to my Reynolds number. Okay, and of course, like a jerk, I didn't plug in numbers for that, so we'll go ahead and do that really quickly. So that Reynolds number equation, if we simplify, we end up with something like this. Okay, we would need to remember the units so that we can correctly plug in, what we need. But there you go. So we end up with something that looks like that. So if I plug in D equals 1, again, this is why I like D equals 1. So 3.40 times 10 to the 5th. So we get 3.4 times 10 to the 5th. Okay, so now we have to go to Moody. So I'll drag a Moody equation over here, or you know what? Let's just go look at this one over here. So zooming it on in, zooming, erasing all this junk. So looking here, we've got a value down here, well, if it will let me draw, okay, of 3.4 times 10 to the 5th. And then over here, we've got a relative roughness of, I believe, 5 times 10 to the minus 7th. Okay, now 5 times 10 to the minus 7th, this is 1 times 10 to the minus, well, let's see, 1, 2, 3, 4, 5. Right, so basically this is so small as to be smooth, okay? Because we're not going to really be able to find a line below that. This 3.4 times 10 to the 5th, well, here's 1 times 10 to the 5th, 2 times 10 to the 5th, 4 times 10 to the 5th. 3.4 is going to be about right here. So again, pull out our trusty dusty ruler, and we're going to go up, as best we can till we hit that smooth line. We'll take a left. Always want to be careful not to forget the left at Albuquerque. And then we're just going to go right along there. Okay. So 0.0015 or thereabouts. Okay, so let's zoom back over. If I don't know really what that's doing there, that's really weird. Let's try that again. Okay. Everybody hates me. All right, I figured something out. I don't really know what happened there. All right, anyway, what was the number we got? I don't even remember. It's been so long. Oh, 0.015. Okay, so we're going to go over here. Okay, F Moody, 0.015. And now we're going to have to use a computer to solve this because 0.015, because I am not going to be capable of solving this particular equation for D. Okay, so give me 1 second. Okay, so using a computer, I'm not 100% sure that I trust this particular computer solution, but is 1.21 feet, which means our initial guess was pretty good. Okay, Again, I don't know how much faith I have in this particular solver, but we're going to roll with it, okay, because it's late at night. The method here is exactly the same that you would do on an exam. The only difference between this and what you would do on an exam is that this particular equation would be something that you could solve, okay? It would not come out this messy, okay? I picked this problem and I didn't work it all the way through, so it's pretty shameful, but that's pretty much what just happened. So yeah, we're going to now repeat the process, and I'm just going to pause it and I'm going to fill this thing out, okay? I'll stop at Moody diagram because I imagine that some of you guys would want to see Moody as many times as possible. I know that my first time seeing this was not a pleasant experience. So I'm going to fill out the next two and then jump back in. All right, so we have these two values here, 4.1 and times 10 to the negative 7. So that's basically still remaining smooth. And the Reynolds number has actually changed fairly significantly. So we have to see it's going to matter. Usually, if the smoother the pipe is, the more it matters. Okay, so 2.8. So let's zoom in, and hopefully we don't get trapped here. 2.8 times 10 to the 5th. It doesn't look like it's going to be too hugely different. I'll do this in a different color. But here's 2. Here's 3. So we're at about, we're going to try to get 2.8 the best we can, which is, whatever. Right in there, maybe. Okay, and we'll take a left. And luckily, it looks like the last time I kind of guessed a little, my guess was a little bit off, but, I wrote down a number that was 0.015. So it looks like this iteration worked. Okay, so that's something to be happy about. So 0.015. So our diameter is going to be 1.21 feet. So we would take that 1.21 feet, and we would multiply that by 12, and we would get 14.52 inches. Okay, so we probably are going to want to order, I don't really know how we size pipes. We probably get them every 2 inches, so maybe a 16-inch pipe if we can get that. Okay, so that's it. Again, don't sweat this. I mean, you'll have to solve for equations like this, but you'll actually be able to solve them. Usually they come out in some sort of like fifth root of, something, something, something. And this one would have, but the minor losses were in there. Okay, so that's what this was. Without the minor losses, we could have solved for this fairly straightforward as d equals the fifth root of blah, blah, blah. And in fact, what I could have done if I wanted to solve this without using a computer solver is I could have assumed that the minor losses were unimportant. And so what you would do there is you would assume the minor losses are unimportant, solve the problem, and then you would come back and you would check to see, you would compare this term right here, this 8.8 times d, to this term right here. I think it's hard to tell based on our current solution, but if I were to plug in 1.21 right here, right, I'm going to get approximately 10. And if I plug in 1.21 right here, well, let's see here real quick, 1.21 to the 5th, right? I don't think it's going to be, I think they're going to be pretty close to the same order of magnitude. And yeah, same order of magnitude. So this one's 12.2. So yeah, we were not going to be able to ignore it on this particular problem. So sometimes you can, especially if the pipe is long enough and there aren't that many fittings, then you know that the friction losses are going to be important. If it's a short pipe with more fittings, well then, so. Anyway, I hope y'all are sound asleep and not awake like me. This lesson took me entirely too long, and I'll do better next time. But this particular problem. This is the map of how you solve a type 3. Minus the fact that I screwed up that last bit. So sleep well, take care of yourselves. Let me know if I can help. I'll talk to you tomorrow. Good night.